Hello, everybody. So I'll begin to go ahead and discuss here with the theory of red-black trees. So since we're done with the AVLP in the separate video, I'll begin to illustrate in this example as well. In this video, the red-black trees. So let's try to go ahead and check what is red-black tree. So this is actually a type of trees. This red-black tree is a self-balancing binary search tree under the binary search tree behavior as well that we're dealing in terms of the binary search tree as what we have mentioned that we're inserting larger value into the right side and then the smaller value into the left side. So a red black tree is a self-balancing binary search tree where each node has an additional color attribute, either red or black. So we are trying to maintain here their color representation. So don't you worry, I'll begin to go ahead and walk you through step by step for this one. And we are preserving the rules and implementations of this red black tree since there will be some rules that we need to follow, especially for the colors, where to when to observe the red nodes and when to observe the um black nodes. So to maintain balance during insertion and deletion operations by enforcing rules that keep the tree balance, guaranteeing actually the logarithmic time complexity for operations such as the searching operation, sorting, and deletion. So here then it is the same with the AVL3 that we're observing with the logarithmic time. Here also we are trying to observe the logarithmic of n base of 2 still because we are dealing with a binary search. So in binary search T, if the n nodes definitely logarithmic of n nodes, then the base of 2, that the answer for that one of the logarithmic will be definitely the possible average of the height of our given binary tree. Now, widely used in many programming libraries for efficient data management. So in terms of the red-black trees, we are trying to use this in many cases. So components of red-black trees, each node is actually each node in red-black tree contains the following: the key value, the data stored in the node. We are also trying to observe, we have the color. Each node is either in color red or black. And each node in a red-black tree contains the following left and right child pointers, which the pointers to the left and right child nodes. This is actually serve as the edges. And we also have the pointers, the parent pointer, where in the edge pointer to the parent pointer to the parent node. Say, for example, the child node is pointing to the parent node. That's actually how does it work. Since we will begin to observe what will be the parent node, the children, the grandchild, the grandparent will begin to observe that later on as we run through with the example. Node coloring in red black trees we are observing here. Each node has a color either red or black. Black nodes provide structures and maintain the balance. So I'm so sorry. Red nodes are used to ensure balance but are not allowed to appear consecutively on a path from root to any leaf. So ang black siya class, this is the basis that since we also do have the nil nodes here, this is the structure of red black tree. Say for example, this is the red trees. This is red black tree. This is black, and this is red. For example, this is red, and this is red. So if this is the case, two consecutive red, that is not balanced anymore. So we can definitely perform a specific rotation or changing of color in terms of that one. How we were able to do the rotation of the AVL3, we'll also observe those rotation, the zig rotation, the zigzag rotation, the zigzag rotation, or the single rotation, or the double rotation. We'll begin to use those approach later on as we ran through with the process. Now, the parent pointer points to the parent node in the three child pointers, two pointers, one to the left child and one to the right child as well. Here then, the parent and child relationship, these pointers are essential for navigating the three structures and maintaining the parent-child relationship, which is the key for balancing during insertion and deletion. So we will begin to observe the parent and child because we will begin to check the parent node and the grandparent node, and then the children or the grandchildren nodes. We'll begin to deal with that later on. We will begin to run through later on as everything. We'll begin to make it basic so that from the I know this is really hard. However, we'll make it easier for you for the sake of your um since I don't want you to deal with a lot of problem. Now, there will be 5 properties that we should maintain in terms of dealing with the red black trees. Node colors. Each node in a red black tree is either red and black. The color of the nodes helps maintain the balance of the tree during the insertion and deletion. So therefore, it will be either represented in a red or a black trees. I mean nodes. And the root property is always black. Ensures a consistent start point for the balancing properties of the tree. So since the root node is always black, so if that will become red, so we have to change that into black position, because if ever that the root property will turns to red, it is not allowed, since the given root node must be always color as black. So that's how it works. Now afterwards, red property, if a red node has children, those children must be black. No 2 consecutive red nodes that are allowed. So as what we have mentioned earlier, if this is red and this is red as well, so therefore this is not allowed, and there will be a certain function that will begin to deal. Is it switching of the color, or changing or we will begin to do the rotation. Don't you worry, we'll begin to observe that as we run through with the example. Since this is also a recursive manner that we have to observe from the leaf node up until the root node. So you will begin to check that's why there is a pointer right there that you will begin to check the child node, and then the parent node, and then the grandparent node. Now, this property helps prevent long chains of red nodes, which could potentially unbalance the tree. If ever it will be a 2 consecutive red trees, that is considered as violations in terms of your red black tree. And then black property, every path from a node to its descendant null nodes must have the same number of black nodes. What does it mean? So say, for example, this is black, and this is black, and this is black, and this is red. So it's okay that there will be a consistent black, but consistent red is not good. Now, for example, here then, you will begin to go ahead and make sure to check here if ever that after the leaf node, there will be a nil node or null node. When we say null node, they are nodes that don't hold any value. They are considered as color black. So therefore here then, it is black, here, black, and black. So as we count the black nodes, certainly it will become 1, 2, and then 3. So therefore it will be 3 here. And for the left side, 1, 2, and 3. So therefore this 3 is actually balance, following the balance property. So that's actually that is really gonna have we will gonna have some fun in terms of that. Now, black property ensures that the tree remains balanced, and the black height is consistent, which helps maintain logarithmic time complexity. So as what we have mentioned earlier, that since we're able to deal with the black trees up until the null nodes should always equal to each of those criterion, the left sub-tree and the right sub-tree, it must equate with the same number. So it needs to be maintained so that it will observe the logarithmic time complexity still. Now, the leaf property, I'm so sorry. Okay. All leaves or null nodes are considered as black. This simplifies the definition of balanced path, ensuring that path from any node to its leaf nodes have consistent number of black nodes. As what we have encountered earlier, that is actually black, and then once we'll begin to count them, the black colors, so they are actually having the same value or the same amount of black nodes in our given left and right subtree. So that is really good from the root node. Take note, This is the one thing that you will begin to always know, that every newly inserted node must be colored red initially. So you will begin inserting the node, and then that is considered initially as red. And then if there will be a consecutive red, there will be a specific this specific discipline that you will begin to observe in terms of that one. Then this ensures that the property that no consecutive red nodes exist, which helps maintain balance during insertion. So if ever that two consecutive happen, we'll begin to make sure that there will be a switching of colors, or doing the rotation if applicable. Now, the common block trees violation. There will be a consecutive red nodes. Two consecutive red nodes. A red node has a red shell. Say for example here then, this is black, this is red. And this is red. Now suppose that you were able to insert this as red. So this is consecutive. What can we do? Since we're able to insert D right now, say for example, you will begin to check the parent pointer. What will be the parent pointer? The parent pointer, you will have to check if there is if there is an uncle, or I mean the sibling of that parent node. The sibling of parent node is C, and that is colored as red, and they are the same, and they are actually in the same color. So therefore, if they are having the same color, we can change them into another color then. So from the red, we can just change that into black. And then once you will begin to check that one, two, and then from the nil up until the nil is 3. And then 1, 2 up until the nil is 3. So therefore, it is balanced still. So that's how you will organize that here. Now, parent node has no sibling. The parent node has no sibling, which may happen when inserting into the leftmost or rightmost side of a subtree. So if ever that the parent node has no sibling, we will begin to do the rotation. It could be a zigzag rotation, or zigzag rotation, or zig rotation. So if ever that there's no C here, then what we can observe, this is red, and this is red, and this is black. What can we do? We will deal with the rotation. This is actually a left. This is left and left and left. So therefore, we can utilize the left rotation. So therefore, it will become B, then D and A. So that's how it works. So that's basic lang. So we'll begin to make sure to run through that process later on. And parent node has no, after fixing other violation like double reds or rotation, will likely fix the structural issue as well. So as what we have stated, we have to perform the rotation so that we can strengthen and maintain the balance of your tree. And red root node, change the root node's color to black to restore compliance with the red black tree properties. So in here then, if the red root node, if the we have to change that into black so that we will begin to observe the implementation that we maintain the black color of your root node. And then balance black height. Path from root node to leaf have unequal numbers of black nodes. The black property is violated. So performs a series of rotations and color adjustment to ensure each path from the root to leaves contain the same number of black nodes. If ever that the black of the left subtree and the right subtree is actually unbalanced, so therefore we might consider there will be a rotation or switching of the color that will gonna happen for the process in the entire process. And invalid black height as well. The black height is not the same for all the root to leaf path. Recalculate the black height from the root to all leaves and adjust using color flips or rotation. So that's what gonna happen. For double black, this is actually occurring in terms of we are removing. It will, for example, if we remove the red one, somewhat it will experience more red, or I mean, if you'll begin to remove black nodes, it will become lesser red. I mean, mag-less na ang iyang black, magdamo iya black can be will begin to experience that one. So double black nodes occur when a black node is removed and its black height isn't compensated for in parent. or sibling nodes. Color flips and rotation will be used to fix double black, and then double black violations by redistributing the black height across the tree. Okay. Now, inconsistent child nodes. A black nose child becomes red inappropriately colored red, like the child is incorrectly colored red while its sibling node is black. So if there will be inconsistent child nodes, we'll begin to perform the color flips and rotation. Perform the correct color flips and rotations to restore the consistency of red and black properties. Wait a second. So sorry. Student is actually chatting. Now rotation to fix structural violation, use single rotation, left or child, left or right, or double rotation, left, right, or right, left. Now the color flips of we will begin to perform after performing rotation, nodes red need to be recolored, changing red nodes to black and vice versa to restore the balance of your tree. And also to start with the standard binary search tree insertion for the insertion operation. Let's try to walk it through, run it through. Start with we will begin to go ahead and make sure to work on that. So start with standard binary search tree insertion. Insert the node just like in binary search tree, comparing values to find the correct position. So in this case, we are observing the binary search tree operation, and then if ever that there will be violation, we'll have to follow specific criterion pertains to that. And fix violation after insertion, check if any red black trees properties are violated. If there will be a red violation, we can perform either flip of the color, switching of the color, or rotation to restore the balance of our binary search tree, or our red black trees rather. Now rotation type, single rotation, double rotation, as what I have stated. We're done with that. Locate the node for that is for the insertion earlier, and this we're gonna have we'll begin to follow the deletion right now. I mean, discuss the deletion. For deletion, we have to locate the node, search for the node to delete, similar to standard binary search tree deletion. So we search that first before we will run through the deletion. And then delete the node. For deleting the node, we have to follow the cases. The case 1, we leave node, we simply remove the node. And then case 2, has one child, replace the node with its only child. And then case 3, has 2 children, find the in-order successor or predecessor and copy its value and delete that. So for in-order successor, just always remember that is the smallest value into the right side. And for the in-order predecessor, that is the largest value into the left side. And rebalance. After deletion, the tree may become unbalanced, requiring recoloring and rotation to maintain the red-black properties. So we have to make sure that if ever that there will be a violation, we have to observe, we have to check that, we have to be mindful in checking and those nodes that we do have, so that we can definitely make sure to correct their position. And then for searching, we're done with the deletion. For searching as well, we start at the root node and begin the search from the root node at the starting point for all the operations in a binary search tree. We have to search from the root node because we have to compare that one by one. If the largest value, we have to compare the target with the current node. And then if the target equals the current node's key, you have to find, you have found the node and the search is complete. If ever that the target equals the current node's key, you have found the node and the search is complete. And if ever the target is less than the value of the current node's key, we have to move to the left position and then you do it recursively. And if ever that the target is greater than the current node's key, move to the right child of the current node. And then you keep on comparing, repeat the comparison keep on comparing the target with the current node until you either find the null or reach the leaf node or the null nodes for that one. Now, if ever that is for the searching, if ever that you were able to find the position of the given element or the key element, you have to make sure to identify where you're able to locate that one in what level. And if ever that you can't locate that one, if you were not able to search the specific element, if that is not if that can't be located into your binary search, into your what we call this one, into your red black trees, therefore that is not there in your tree. So what can you do? You just have to make sure to identify implement that the given node is actually not um into your tree. Now, for the time complexity, it will be the same thing with the AVL3 that we are trying to also maintain the logarithmic time complexity. Time complexity of red-black trees refers to the efficiency of operation like insertion, deletion, and search in relation to the number of nodes in the tree represented as n. So, logarithmic of time for all the operation, this is because the red-black trees is self-balancing and it ensures that the height of the tree remains logarithmic. All this operation, insert and delete and search, are dependent on the tree's height. So in this case, actually, for example, you do have the numbers of the nodes, for example, 8 numbers of the nodes. Since we are having the logarithmic of time, logarithmic of 8 with a base of 2. So say, for example, how many multiplication that we'll begin to deal until such time that we can occur into the 8. 2 times 2 is 4, that is 2 already, and another 2 equals 8, so it is 3. So that means to say that at least 3 height of your given binary tree will be observed into your red black trees. That's how it will be implemented. Now, why is that logarithmic time? For the logarithmic height, the height of a red black trees is kept at logarithmic level, specifically at most 2 times the logarithmic of n, where n is the number of nodes, as what we have mentioned earlier, that we are observing the logarithmic of n base of 2. That's why it is being implemented right here. So the balancing properties of the red black trees is actually such as no two consecutive red nodes ensure that the tree doesn't become unbalanced, straight line like a linked list. So we are trying to observe that we cannot perform any degenerated trees. When we say degenerated trees, those are the skewed trees. Those are the the left skewed and the right skewed. We have to make sure that we were not able to observe those cases. If ever that there will be a skewed trees, we have to perform changing of the colors, or if rotation, if applicable, we can do so. And then, for the worst case height, if we're not able to observe the height of the tree is at most logarithmic of time with a base of 2, because the worst case will always maintain that logarithmic time, since we cannot have any degenerated trees here then. So because the red black trees property force the tree to remain balanced. Now, the logarithmic height, a binary tree with a height h, has at most 2 times 2 to the power of h nodes. Say for example, we do have 2 height here then. So what can we observe that has at most 2 to the power of h? So 2 to the power of h, that is 2. So 2 times 2, that is 4. So 1, 2, 3, 4. So therefore, we do have 4 nodes that we do have right now. So that is really correct. For a tree to have n nodes, the height must be proportional to the logarithmic time. In a red black tree, the height is controlled to remain at most logarithmic of n base of 2, ensuring that all operations take logarithmic time. So don't you worry, class. You will not begin to focus into the time complexity because it will be dealt into in terms of the algorithms and complexity classes as well. Since this is just a structures of the data structures and algorithm, this is just a fundamental for all of those computer science courses as well. And if you're IT and EMC and IS or what program, this is the foundation of the other subject. If ever that you will begin to deal with the machine learning, with AI in the future, and also other subject, other courses, it is really one of the foundations that you will begin to observe. Now, keeps operation efficient for the self-balancing. The advantage of the red-black trees keeps operation efficient with logarithmic time complexity. Less strict than AVL trees. Red-black trees allow for less strict balancing, which often results in fewer rotation during insertions and deletion, because we can just simply change the color respectively. If ever, we can just simply shift the color. Useful in situations where there are frequent insertions and deletion, such as in databases, real-time systems, and memory management. Those are the applications of red-black trees. And we can also, that is also being used in databases, indexing to maintain the order set. And that is also being used in memory management for managing memory blocks in system requiring fast allocations and deallocation. And we are also using that in real-time system used in systems where balanced tree operations are crucial for maintaining system performance. So those are the end of our topic for the red-black trees. I hope so that you were able to understand how does that work, and if for the implementation of the insertion operation and deletion operation and search operation, don't you worry, I'll begin to create a video separately for that one. I'll be going to give the to you the specific example which is really manageable. I'll begin to illustrate to everybody how can we make sure to maintain the balance in terms of working for the red-black trees, AVL trees, as well as the display tree. So we'll begin to focus those trees as for now. So I'll begin to leave a quiz pertains to that in your MS team. Once you were able to listen and understand this video for the introductory of red-black trees, you should comment down below that you understand, or what will be your what will be your understand, what have you understand in terms of red-black trees. And all of the student must answer in 1 to 2 sentences respectively, and there will be a point for that, as there will be a points pertains to that, additional points into your quizzes. Now, you should make sure to comment in that in this video, at least, for example, 2 to 3 sentences. What will be your takeaways? And of course, your takeaways must not be the same into the other student. If ever that you're actually the same with your classmates, of course, automatic 0 into your comment. So that is considered as part of your quiz, since if you're not trying to understand this video, it is not my problem at all, since we cannot handle any face-to-face case class this week. So this is just a run through for our classes. So thank you so much, everybody. I hope so everything's clear. And I will not be going to post this instruction in your teams because it will not, I don't want to give hint that there is a quiz in my video. Thank you so much, and bye for now.